In this lesson, we'll find and explain patterns with natural numbers. We'll do numeric patterns, shape patterns, and patterns on the number line. We'll use difference tables, visual reasoning, and formulas to get to the nth term. This lesson has several worked examples and moderate difficulty problems, so follow along step by step. Example 1, an arithmetic pattern. Here is the sequence 7, 12, 17, 22, and so on. We'll find the rule and the nth term. Notice how each term increases by the same amount. We see the difference is always 5. When the first difference is constant, the pattern is arithmetic, and the nth term is a linear expression. If a sub 1 is 7 and the difference is 5, then the nth term is 7 plus n minus 1 times 5. In math words, that's 7 plus 5 times n minus 1. Example 2, a quadratic pattern. Consider the sequence 2, 6, 12, 20, 30. We'll use a difference table to determine if it's quadratic, and then find a formula for the nth term. We observe the second differences are constant and equal to 2. When the second difference is constant, the sequence is quadratic, so the general nth term has the form a(n squared plus bn plus c. We'll solve for a, b, and c using the first 3 terms. Solve the system. From these 3 equations, subtract and simplify to find a, b, c. Solving gives it equals 1, b equals 1, and c equals 0. So the nth term is n squared plus n. Another way to write it is n times n plus 1. Example 3. Triangular numbers, a classic shape pattern. We'll draw dots to form triangles and then show a visual derivation of the formula. Triangular numbers count the dots needed to make an equilateral triangular array. 1, 3, 6, 10, and so on. Now, the visual trick. If we take 2 identical triangular dot arrays and put them together, we form a rectangle. 2 times the triangular number equals n times n plus 1. So the triangular number equals n times n plus 1 divided by 2. In words, that's n times n plus 1 over 2. Example 4. Square numbers and how odd numbers build squares. The first few squares are 1, 4, 9, 16. Notice the differences are odd numbers. 1, 3, 5, 7. If you add the next odd number to the previous square, you get the next square. We'll animate this idea with dots. Example 5. Patterns on the number line. Suppose we look at numbers that leave remainder 2 when divided by 5. These are 2, 7, 12, 17, and so on. On a number line, these points repeat every 5 units. We'll mark them and give the general formula for the nth such number. Example 6. Polygonal numbers, hexagonal numbers. The sequence goes 1, 6, 15, 28, and so on. We'll use differences to recognize a quadratic, and then show the standard closed form h sub n equals 2n squared minus n. Strategy summary. To find rules, try differences, visualize arrays for shapes, and translate repeating patterns on a number line to an arithmetic formula. Here's a harder practice with guidance. Find the nth term for the sequence 3, 10, 21, 36, 55. We'll use a quadratic ansatz and solve. The second differences are constant and equal to 4. That means the general term is quadratic. a(n squared plus bn plus c. Solve by substitution using the first 3 terms. For n equals 1, we get a plus b plus c equals 3. For n equals 2, we get for a plus 2b plus c equals 10. For n equals 3, we get 9 a plus 3b plus c equals 21. Subtracting shows it equals 2, b equals 1, and c equals 0. So the formula is 2n squared plus n. To wrap up, here are the key takeaways. First, if first differences are constant, you have a linear rule, an arithmetic sequence. Second, if second differences are constant, you have a quadratic rule of the form a(n squared plus bn plus c. Third, shape patterns can often be explained visually and lead to closed forms, like triangular numbers and square numbers. Finally, number line patterns repeat with a fixed period, and we can write them as arithmetic rules. Practice these methods: differences, visual pairing, and algebraic solving, and you'll be able to recognize most natural number patterns quickly. Thank you for watching, and keep practicing.